Okay, so we'll go ahead and start here. And some of this we kind of jumped the gun and we talked about a little bit because, as I said, it's the one thing I disagree with this book on is the way they introduce everyday forces. You're dealing with normal force and force of gravity before they tell you that those exist, which I think is dumb. So this is kind of a rehash of what we did early on. And some of you are finding it, like mass and weight, and you've known this, they're not the same. If a problem says weight, they mean force of gravity. They mean F sub g, which is mg. Weight is different on different planets. You know that we had a problem in chapter 3 where a robot on Mars drops a camera off a cliff. What's acceleration due to gravity on Mars? Because acceleration due to gravity is different, weight is also different because g sub Mars is not the same as g sub Earth. It's always directly down, we know that, and it's shown as F sub g. Normal force is, and I talked with a couple of you about this, it's generally opposing gravity. Okay? Normal force exists when there is a surface on which the object is sitting. Normal force doesn't exist if an object's on a string. Normal force doesn't exist in a whole variety of other situations. It exists when there is a surface that is pushing back upwards on that object, and that's what's keeping it from hurling towards the center of the Earth rapidly. This, I say with reservation, equal in magnitude to gravity. Not always. So your book says this in the chapter. This is actually just my summation notes. But not always. And you're already finding some cases, like when something's on a slope, where the normal force is only equal to a portion of gravity. There are cases where normal force, we're going to come up with these cases soon, is equal to more than gravity. So there are some exceptions to that. Now, for an object sitting on a perfectly flat plane with no other forces on it, it's not being pushed on, it's not being lifted, normal force equals gravity. But anytime that you've got an incline, all the stuff that we talk about on ramps, normal force isn't equal to all of gravity. In the case of a ramp, generally what we see is that if this is gravity and this is F of gy, in these cases, normal force tends to be equal to only the F of gy portion of gravity. Now, we're going to start getting into a lot of things pulled on strings at angles, and next week you'll be doing your frictional forces mini lab, and you'll be pulling things on strings at angles. And that also changes the amount of normal force that's there, because you're changing the balance of forces on the y-axis, and the normal force changes. Okay, we designate it as F sub n, and I guess it's supposed to be a lowercase n, and I might have been doing an uppercase n. My apologies. I'll go back and double check my source. We'll hit other stuff about normal force as we go. Friction. This is the whole next section. So 4C problems are just sort of computing friction. 4D are really overcoming friction. So you've all encountered friction. Without friction, you can't move. Yes, friction generates heat. If you are walking on a frictionless surface, you're going to fall down a lot. Ice is a relatively low friction surface. Without friction between your tires and the road, you can't drive. If you've ever hit an icy patch, you know what happens. You just go sailing. Same thing with your foot. You hit an icy patch. There's no friction between the two surfaces that are in contact. You can't walk. So friction opposes force applied. Friction has got oppositional defiant disorder, in essence. It is always in opposition to the force that's being applied. Doesn't matter what direction that force is in, friction opposes it. There are two kinds of friction, two big categories. There's static and kinetic. Static, typically means still, steady state kind of thing. And static friction is what keeps something from beginning to move. So if all of you very gently with your fingertips push on your desk a little bit so it doesn't actually move, but you're exerting some force, like push it forward. You're exerting force on it. if the desk is not sliding forward, static friction is what's keeping that desk in place. Up to the point when something starts to move, so you can push very lightly on the desk and a little bit harder and it's probably still not moving, and a little bit harder and it's probably still not moving. Up to the point where it breaks loose, the amount of static friction is equal to the force that you're applying. So up until the point when that object would start to break loose and move, and I heard a few desks start to squeak forward, so you overcame static friction. At the point that you're pushing and nothing's happening, you have not yet overcome static friction, and static friction is equal and opposite to the force that's being applied. So up until it starts to move. Once it starts to move, we're outside the realm of static friction.
So static friction can never be more than the force being applied to the
Nope. Nope. Now, the maximum static friction, the point at which the object breaks loose and starts to move, is very often, up until you get to the point where it breaks loose and starts to move, that maximum force of static friction is greater than the force that you're applying. But the static friction that's actually coming back at you, in essence, is equal to your force. So, good question. Other questions on that? Yeah. Okay, comment, observation? Could do that, yes. Okay. Kinetic. So you know that kinetic means motion, things in motion. There is friction between any two objects. And friction, to sort of back off to what it is, every year some, really clever, usually sophomore, comes up with the whole dude, do you know that you can never really touch anything? Yes, sweetheart, I do. No, really, the microscopic surface of your finger and the microscopic surface of a desk, you never really touch it. Yes, I know. Get over it. But at a very microscopic level, all surfaces have roughness. And so friction is it's an interplay at an almost molecular level between two surfaces. And the roughness of those surfaces is what creates friction. So, sandpaper is a high friction surface. Ice is a very low friction surface. And it has to do with the microscopic characteristics of the surface. So, we don't have a frictionless surface. Even ice has some coefficient of friction. It's really low. But all the physics problems that say you're on a frictionless sliding board, baloney. No, you're not. But we like to pretend in high school physics and in college physics that friction, that we can ignore it. And we do ignore it sometimes. But everything has a frictional component. Air has a frictional component. Air resistance is just friction of the air. It's the friction of an object moving through the air. So kinetic friction retards, it reduces, it slows down motion. It doesn't prevent it, though. Now, the rougher the surface, of course, the more friction you're going to have. So here's the critical thing. Once you get something moving, the force applied exceeds the force of static friction max, it starts to move. At that point, if we're only dealing with the one axis, the net external force is just the applied force minus that force of kinetic friction. So, for an object that is moving with zero acceleration, what's the relationship between kinetic friction and applied force? Equilibrium, which means what's the relationship between kinetic friction and applied force? They're equal and opposite, yeah. At the point when something is moving with constant velocity, is there still friction on it? Yes. But that kinetic friction is equal and opposite to the applied force. Does anybody here, I got a car now that has the little instantaneous mileage thing, and I'm a geek about driving for mileage. Have you seen vehicles that have, You know, they might have the push button and you can do miles to empty or instantaneous mileage or average mileage. So if you have a vehicle like that, or you know somebody who does, drive around for a week, just 1 week, with that set to instantaneous fuel mileage. And what you're going to start to see is the force relationship. How much work is the car having to do to maintain a velocity? So on a flat level road, going 50 miles an hour on a still day, in other words, no wind coming at you other than what the car moving through air is generating, you can get that instantaneous mileage up to, in some cars they show infinity, mine shows 99.99. Because it's not taking, you take your foot off the accelerator, and in the moment where you're still maintaining constant velocity, your car's not having to exert a whole lot of effort to maintain that speed. The road starts to slope up a little bit. You have to push down on the accelerator more. The car is having to apply more force to overcome now force of gravity on the X, because you now have a component of force of gravity on the X, and the frictional force doesn't change. Okay, if the road surface changes, so we go from brand new blacktop to tar and chip, higher coefficient of friction, more kinetic friction on a tar and chip road than on a blacktop road. If you happen to be driving on ice flats someplace, as long as you're going in a straight line, you can pretty much lock up the tires and continue at your rate of speed, which you don't want to do on a real road. Anyway, it's a nice little experiment to see, think about effort and sort of energy and force exerted. If you're at ma equals 0, zero acceleration, kinetic force and force applied are equal to 0, and we should write that out. If ma equals 0, in other words, yes, you're at equilibrium. Okay, so how many of you have ever pushed something to get it moving? A big box, a piece of furniture? Good. It generally takes more oomph to get it going than it does to keep it moving. Don't let that stop. Keep it moving, keep it moving, keep it moving. The force of kinetic friction tends to be smaller than the force of static friction for any given surface object pair. So if we fill a cardboard box with bricks and stick it in the hallway, it's going to take more force to get it moving than it will to keep it moving. And this is what we were talking about with friction and surfaces. It's all about the quality of the two surfaces. Pushing something across deep shag carpeting versus a hardwood floor. Totally different equation. A tar and chip road versus a smooth asphalt road versus ice. The ice road truckers come to mind. For every single surface pair that exists, we can calculate a coefficient of friction. And we get to use our favorite little symbol again, mu. The Greek letter mu. I still have to dig out all my chemistry and physics cartoons because I have several cat cartoons that involve mu. Yes. And mu is a ratio. Just like all the trig functions are ratios related to angles, mu is a ratio. And it's the ratio of the force of friction and the normal force in each case. So we're going to be spending, as you might imagine, a fair time calculating coefficients of friction. The ratio stays the same. Even when the mass of the object changes, even when if you push down on something, the coefficient of friction stays the same. The force of friction may change, but the coefficient of friction stays the same. Okay. So when we have the coefficient of friction and we have the normal force, we can always calculate force of friction. You might begin to suspect that the fact that we have this new thing, whoops, is going to mean that we have one more thing to build expressions with. You'd be right. So basically we're going to start to get into problems where you have to build expressions using this coefficient of friction. Okay. So let's go ahead and we'll do the sample problem together. You don't have to have a book for this. And then I will assign 1 through 3 on 4C. So 1 through 3, 4C, page 145. But let's do the sample problem together. So we're told we have a 24 kilogram crate that's initially at rest on a horizontal floor, and it takes 75 newtons of horizontal force to set it in motion. Find the coefficient of static friction between the crate and the floor. So where do we start? We start in the same place we always start. We start with a force diagram, free body diagram, I'm sorry. So F sub G, Fn, and we know that we have, whoops, the force of the pusher to get it moving is 75 newtons, which means, what else do we know? That the force of static friction max is equal to what? 75 newtons.
Or do we think it would?
Well, yeah, it's negative
Okay.
75 newtons, you're right. So what we want is the coefficient of static friction. So let's write down this. Do we have the static friction max? Yes. Do we have the normal force?
Yeah, it's just.
We don't have normal force, but we can create an expression for normal force. So if we look at a sum of forces on our y-axis, we know it's 0, and we know it's equal to Fg plus Fn, so we know that Fg equals negative Fn. Or we can say, it's probably easier to say negative Fg equals Fn. Let's do that instead. Okay, so what we can then do is take this and plug it in there. So we now have mu s equals force of static friction max divided by the negative of Fg. I'm going to shrink all of this. So that's equal to Fs max divided by the negative of mass gravity. Okay, so we've got 75 newtons divided by, no, negative 75 newtons divided by 24 times. So we get a mu sub s of 0.318, and it shows up as a negative 552497. This is a, what are the units here? Newtons divided by newtons gives you what? Nothing. They cancel. It's a ratio. What is true of ratios? They're unitless. Oh, I love the groan that always collectively goes up when we say that first time. Ratios are unitless. So this is a unitless ratio. So the correct units for mu are none. So we would, and also we take the magnitude of this. So we would say that mu equals 0.32. And it causes me physical pain to not write a unit there. Even though I know it's right. I'm so ingrained in like, write the unit, write the unit, write the unit, write the unit. Where's your units?
You could say they're munitless.
Ah, you could say they're munitless.
I cannot believe you just said that.
Thing of beauty, Zach. Thing of beauty. Those are pretty simple. So as you finish with 4B, start on the 4C book. We'll do those. We'll work on those tomorrow. Pardon? We ignore it because it's magnitude. Sorry. I know.
Everything now. We're ignoring negatives, ignoring
We're not ignoring units. They canceled. They canceled. We are not ignoring them. The negative, however, yeah, I got no good answer for you on that one. Sorry. I'm sorry. Once you get your answer, it's magnitude. It's the magnitude. Okay, that's it, folks.